So, hello everyone. Thank you all for coming today, and also thank you about the chance for me to present our work. Before I begin, I would like to thank my supervisors, Ninh Pham and Richard, and also members of the faculty and members from ESR. Glad to meet you guys today. And our project is about compact segmentation methods for mobile computer vision. The motivation of our project is COVID-19 poses a huge challenge to the globe, and accurate testing of it is vital to the treatment and further prevention of the infection of the pandemic. But accurate testing normally involves central testing labs, and ESR participants in the process, and they witness how the long turnaround time of transporting sample tubes to central labs causes delays in efficient detection. So the data science team developed the idea to build a point of use diagnostic process. They're thinking like, what if we exclude the step of transporting? To verify the idea, based on the photos of testing tubes taken at the lab, they train a segment model to segment the tip of the liquid and the tube body, which is yellow color in the image, to as a basic word for the further development. And they use the TensorFlow JavaScript to integrate the model into the web application so that it can be run on mobile devices. However, in practical experiment, though the model performed well in accuracy, it costs too much memory, time, and computational resources, making it not suitable to actually run on a mobile device. And that's how we get the aim of this project, to provide more compact segmentation models that have a good trade-off among these factors. And we can have a look at the product first before we dive into the methodology and experiment. So the product is called Glow, and as you can see, it can be run on the browser of the mobile phone. Here, by choosing an image and by choosing the models, you can see that we clip into a sample image first, and after that, there are many models you can choose. That's the models we uploaded into the web application. And after you choosing one, and click the predict, sorry about that, and click the predict, the model is actually loaded into your own mobile phone instead of run on the cloud platform and give you the result. And here is another model. This one is smaller, so it gives a quicker result. So we can see that different models, some produce more accurate result, while some do a quick inference. That's the point we need to choose between. And we can now get into how we make it come true. The previous relevant work includes suitable model for the task, and UNet is a popular one for medical images. We can see that it has a U shape, and another unique thing is that it can be combined with others in the model to form different styles. And how it works is we can split it into two parts to understand it. We can see it reads into the original image and produces the desired output. And in the output, it recognizes three classes. One is the tip in blue color, and one is the tip region in yellow color, and the third is the background in purple color. How it makes it come true is that it has two parts, the encoder part and the decoder part. What encoder part does is it learns the features and extract features, and the following decoder part construct the designed segmentation output from the feature it learns. And what's special about UNet is that it also introduces a skip connection, which is the concatenation here that combines the output of the encoder with the output of the decoder. And by this way, we are able to keep some lost information through the encoding and decoding operations. That's the point to make UNet produce more precise result. However, due to our dataset, our dataset is not big enough for training a large model. So we want some pre-trained weights that are suitable for computer vision tasks. And what we choose to do is that we use transfer learning to have a pre-trained part, which is the encoder part here. We can see that it replaces the original part with the mobile net v2 model. And through this, we are able to have the function of the mobile net v2, but also make it suitable for our specific task. After we have the baseline model, our next question is how can we keep accuracy and progressively simplify the model? And luckily, there is a hyperparameter called width multiplier, which was proposed in the Mobile Nets article. It was used to adjust the filter numbers in models that train from scratch. But here we choose to use the width multiplier, which is the alpha here, to adjust the size or the filter numbers in the trainable parts of the model. And by this process, we're able to get our proposed model. We call it alpha MobileNet v2. The benefit of it is if we change the alpha, we're able to get a series of different models that they are with similar structure, but we can progressively simplify it. However, although shrinking the alpha can reduce the complexity, but the locked pre-trained part, which is the encoder part here, it becomes a limiting factor of our process to do the experiment. By observing the right chart here, you can see that the orange trainable parts get smaller and smaller and approaches zero, but the non-trainable parts stay largely the same, and it is from the parts in the MobileNet v2. So we're also thinking about what if we have another more flexible model that can show a more significant adjustment. So we choose to experiment with another structure called UNet exception style to form the alpha exception model. And here we can see, since the model, all of the parts is trainable, each time we reduce the alpha to half of its original size, we're able to reduce the total parameter about or nearly 1/3 of its original size. And here comes to the experiment parts that our data set has about 628 images. It's not a quite large number. And we choose to divide it into testing and training set with a ratio of 20 and 80. And we train the model with two methods. One is train the models on the complete training set. The other is we further split the training set into a validation set. The metric we use here to evaluate the accuracy is called IOU, which is commonly used for segmentation task. It calculates the area of intersection between the ground truth image and the prediction image, and divided by the area of union. And here we can see we use two individual IOUs for each the tube region and the tip region, and also two main IOUs that calculates the average value of IOUs of tube and tip and background, or the average value of IOU for only the tube and tip, which is the column here. To better understand the form, we visualize the results. And we can see that for the larger tube region, actually all of the model have a good performance, that many of them are above 80 or even 85. And or close to the 80. But when it comes to the IU for the tip region, which is smaller in the image, all of the models suffer loss in the accuracy, but with different degree. It is especially obvious when the alpha reduced to 1/32, which is quite small in the alpha mobile net v2. And for the time performance, we invite volunteers to run our models on their own mobile devices, and for each run, it will perform 294 predictions on 21 images. And we will take the average for each record and then group the data by the model ID and mobile device type, then form the summary plot on the right side. Here we can see that the first group of data is from the baseline model, and compared to the baseline model, all of the proposed model actually show a significant improvement in time performance. And the right four models here they were proposed in a later phase in our project, and all of their data were collected on the same device. We will have a more detailed analysis in the next slide. Since we have two aspects to evaluate, which are the accuracy and the time performance, so here we choose to use two plots, but all of the column is from the same model, that we can have a clear look of how these two metrics compare to each other. And about the accuracy, all of the accuracy goes through a smooth decrease as the model gets simplified. And about the time performance for each series of alpha model, the left series are from alpha mobile nets, and the right series are from alpha exception. Within the series, the model shows a right skew in the time reduction. And that's our observation, and also is what we will consider if we want to choose one model to use. An additional interesting observation is when we compare the 1/16 mobile net v2 model with the UNet exception model. Although they have almost the same size, but the previous one has twice the time consumption as the later one. So it actually verifies that when it comes to the time performance, it is the number of operations matters than the parameter in the model or the size of the model. And finally, we'll have a look at how these prediction images are. We can see each group has 6 images, and the first one is original image, second one is the ground truth, and third one is produced by the baseline model. And all of the 3 image downside are predictions produced by our proposed model. For the image only containing one single turbinate, all of the model perform quite well. But when it comes to multiple tubes in the image, then the alpha mobile net v2 still keep a good performance, but the alpha exception somehow suffers a loss. So it leads to our future work of this project that MedAI released the Segmentation model in April this year, and it actually produced quite good result of segmenting images and produce the objects. So if we can use more reliable ground truth images, we may be able to improve the current model. The other aspect is we can see that compared to the tip region in the image, all of the models suffer a loss in accuracy when it comes to casting the tip region, which is smaller in the image. So if methods can be taken to address the problem of imbalanced target region, maybe we can also improve the accuracy. And here are some relevant resources. That's my presentation. Thank you very much. also any questions?
Do you have any insight for why when alpha is set to 1/32 there's such a big
Yeah, that's a actually like the question because yeah, I'll go back to here. Maybe here, yeah. So I have some plots that I haven't put it here, but it's the training process of the loss value and the accuracy during the training. And we observed that when the alpha reduced to 1/32, it actually shows a different pattern than the previous models. Yeah. So that's an interesting observation that also the reason why I put it here. But we didn't take further steps into digging into the reason behind it. Yeah, so thank you for asking this.
First time I've seen IOU as a measurement. 100% 's ideal.
Oh, sorry?
The IOU measurement that you
Yeah.
come up with is the ultimate idea to get that as up to 100%. I just wasn't sure about what that actually measured.
You mean
Yeah.
can we make it into...
100% is what you want, yes?
Yeah, so ideally,
Okay.
I think everyone wants a
Right.
high accuracy like that. Yeah.
When it came to the time performance, I just didn't understand what the time was. Is that minutes?
It's actually seconds. It's like the ms.
So, yeah.
So it's like the time. The metric here for the time is the time to do each prediction, to do each inference.
Right.
Yeah.
Okay.
Yeah.
So when does that, depending on time measurement, when do I worry about it? If it's going to take me 5 hours, I'll worry about it.
Yeah, that's for sure. Yeah, that's also the reason we want to conduct this project. Yeah, to make it really suitable to run the mobile device instead of crashing the website like that. Yeah. Cool.
So you seem to be using quite a big tool for quite a specific task.
Yeah.
Because the task is just like separating
The
liquid
tip
from
and
the
tube region. Yes.
I'm wondering whether there is a lighter weight or more traditional approach to this problem rather than just directly bring on these pre-trained models, these large models, because your goal is to make it lightweight.
Yeah, that's also a vital point because what we did actually for the Alpha Mobile Net V2 model, this one it has a pre-trained part, which is the laptop part. But for the Alpha exception model, sorry, I should present it more clearly. This one is actually trained from scratch. So this one it doesn't have a pre-trained weights in it. That's also the reason why this model is the quicker model in the previous video I showed here. Yeah. So because what the Alpha did is it adjusted the channel parts, and in here all of the blocks are blue that I made it deliberately to be seen that all of the parts in this model is channelable, but in here only the blue blocks here is channelable. Yeah. Also, thank you for asking me this.
Sorry, I have one more question.
Yeah.
I only just realised, did you remove the skip connections when you went to your fully trained from scratch model?
Sorry, pardon me?
Oh, did you remove the skip connections?
Skip connection, yeah.
Yeah, okay. Sorry, I just hadn't noticed. I have no question.
Okay. No worries. Actually, if you ask this, actually, the different thing about Alpha exception is that it implements the skip connection by residual connection.
Yes.
That's the reason I use a different color in this model compared to the previous one. Yeah.
And it's doing like the resonate short skip.
Yeah, exactly. Because here the skip connection were implemented by the concatenation operation, but here it is implemented by the residual connections.
Yeah. Interesting.
Yeah. Nice question.
Did I get it right? Like the classification for multiple tubes is poorer than the single tube.
Yeah.
So
That's true.
what's your recommendation here? Do you want to continue to optimize for multiple tubes, or do you want to have a pre-processing step where you just break the image?
Yeah. Also, thank you for asking this, because my supervisor discussed with me that maybe we can do something like we split the individual tubes before we do the prediction. Like we can split the each tube from the multiple image before we do the prediction. That is indeed a method to improve the performance, but that's a different process. But also it is doable. Yeah, if we have time to improve that. Cool.
Okay, thank you very much.